right, so today's session is a session related to when to use which instrument. There are a lot of choices in terms of geometry and other variables related to instrumentation, and it can be very confusing in terms of when to measure what material with which instrument. And so what we're doing in this WebEx is providing a foundation to help you understand when to use which instrument, what kind of instrument you should use. Now, as we got into this, we realized this was a very large topic, and we're not going to be able to cover everything in 1 hour. So what we've done is we've built a methodology that we can apply to different types of materials. And you'll see we've documented a number of these materials, but we're going to be adding more over time, so that depending upon the type of material you're having to deal with, you'll be able to go to our manual and look at the materials that we've documented and maybe not have to go through the methodology to see which instrument is best for this material, because we would have already done it. So with that, if you guys have materials that you want to apply to this methodology, please feel free to send them our way, and we'll add them to our database. So the agenda today is, obviously with printing devices today, we can image on all types of material: paper, plastic, acrylics, different textures, depth, gloss, sheen, all which affects how our eye sees the resultant color, which means it's a challenge to find an instrument that can actually measure the sample and capture what the eye perceives. And that's part of the reason why we have so many types of instrumentation. This is very challenging. And as far as I know, this is one of the first attempts to simplify this process of understanding which instrument to use with which material. Now, you won't find this information anywhere else. And so at some point, we'll be putting this content in a place where it's only available to our users or our subscribers. Now, before I get too far into what I'll call traditional spectrophotometers, I want to bring up technology that we've been working on for a couple of years based on the ChromaChecker Nano instrument. This is a little handheld instrument, and it's unique because it measures both texture and appearance. It's a colorimeter, but what we've done with this instrument is we've added the capability to, if you take a look at these green squares, these are pictures of the same green paint on different textures of material. And when you look at there's a difference. And part of the difference is color, due to the texture of the material that this color is being applied to. And so we've instituted this concept called dominant color. And dominant color is different than the average color. Every time you measure color with an instrument, it's doing the average of the color it sees within the aperture. So that's kind of how every instrument does it. But it doesn't necessarily reflect on how your eye sees the color, where dominant color does reflect on how the eye sees the color. And with this functionality, you can have both average color and dominant color tolerances. So it's kind of a new concept related to managing color, but I think it's definitely valuable because, as I've said, sometimes it's not the average of all the colors in the aperture you want, but the dominant effect of how your eye sees those colors. Now, this instrument also sees and can recognize textures and patterns. So these brown squares here are actually wood patterns. So you can actually measure a sample of wood and then put a tolerance on what's called surface match, so that, and this is independent of color match. So you can have a tolerance on color match, and you can have a tolerance on surface match. And so if you're measuring natural materials like marble, that surface match is 89%. This wood match is 85%. This textile match is 92%. This aluminum match is 82%. So in this way, you can have different tolerances for what constitutes a visual surface match between any two materials. And then there's a couple other parameters, including uniformity match, where it's actually comparing the pixels within the aperture to one another and making a numeric score in terms of how well they match. So if it's a flat surface of all the same color, like the same paint, very low uniformity number, where if it's a lot of different pixels and a lot of different colors, a lot of different CMY rosettes, things like that, you'll have a much higher color. Because again, from an appearance standpoint, the color is one thing, but the appearance is something entirely different. And so we've already done a fair amount of work at putting ratings and scores on metrics that are outside of color. And so I bring this instrument up because it's been kind of an experiment, and we've got a number of customers using it for things like ceramic tiles and even other unusual types of material like makeup and things like that. But I wanted to call this out. And if you go to chromachecker.com/nano, N-A-N-O, you'll learn more about this instrument. But today's session is more related to spectrophotometers. And when we talk about spectrophotometers, there's a lot of variables, such as the geometry of the spectrophotometer, the illumination method, the type of automation, the measurement modes, and aperture sizes. So in this presentation, we're going to go through some of the key differences here and what they mean and how it can help you as you understand more how the instrument works, how you can apply it to know which material to use it on. The majority of instruments on the market today are 45-0 instruments, which are really good for measuring flat, regular surfaces where the light is illuminated, in this case, from straight over the object, and then it bounces off the object at a 45-degree angle, and the detector captures that color and breaks it into the spectral distribution curve and figures out what color it is. There's also 45-0. There's also a 45-0 where the light is annular, meaning it's circular. It's coming from all around the sample versus one point from the sample. And a typical sample of this is like an i1 Pro 1. The light came from essentially a tungsten source from a point. The i1 Pro 3, it's actually annular, and the light actually is illuminated almost 360 degrees around the entire sample, and then it's reflected up at a 45-degree angle and captured, which is a great improvement in how that instrument measures color. Now, with 45-0 type instruments, there's what are called measurement modes, which has to do with the type of light that is illuminating the subject. And ideally, you want that type of light that's illuminating the subject to match the type of light that you're using to illuminate the subject with your eyes. So you want to ensure that the two are the same. And hence, the industry's come up with 4 different measurement modes to accommodate the different lighting that can be used to illuminate. And then, of course, the aperture size is also a variable. Some instruments have switchable apertures. I'd say most instruments have one built-in aperture. And we'll talk about when you would use different apertures for different applications. Now, the next instrument we're going to talk about, the type of instrument, is called a D8-degree sphere. Typically, these have been very expensive instruments in the past. We've introduced a D8-degree sphere because so many of our users are measuring material that requires a sphere instrument, which we'll talk about more a little bit later in the presentation. But essentially, the way the sphere works is that the data that's being illuminated can scatter at any angle, and the instrument still picks up the data. And typically spheres have both a spin and a spec option. And typically the spin option doesn't consider the surface or texture or gloss, where the spec does consider the visual effect of the surface and gloss. And again, we'll show an example, a couple examples later of when you might want to use spin versus when you might want to use spec. And again, you have aperture options with a D0, here we're talking about a D0 degree sphere, which is a device like the Spectra 1 from a company called Variable. Now, we also have a D8 degree type of sphere instrument, which this is our CC sphere that you'll find on our store, our website. And again, it's both spin and spec options to accommodate different surface characteristics and whether or not you want to incorporate the gloss and the texture in the actual measurement or not. Then there's also multi-angle instrument applications where you have sensors at different angles picking up the scattered light that's being illuminated down on the sample. And typically these are very expensive instruments and very proprietary, often used for things like metallic and speckled auto paint, where you have paint where it refracts the lighting from all different angles. Now, let's talk a little bit about some general rules. We're going to start with aperture size. And the aperture size is affected by the line screen of the print that you're imaging. The lower the line screen, meaning the more coarse the line screen, like typical newspaper is 65 to 100 line screen per inch. So you see the dots, they're very large dots. In that type of printing, you want a larger aperture to capture the color. You don't want the dots to unjustly bias what the eye or what the instrument's actually seeing. As you get into higher quality printing, which is what most digital printers and most conventional printers work with today, you can get by with a 1.5 aperture size instrument. But it can also be, in some cases, too biased, because if the actual material that you're measuring isn't consistent, like 100% consistent, you can have some fairly large delta E's by measuring a small aperture across the same color patch, just because that color patch is not consistent. So ideally, if you wanted the most accurate color rendition of what you're measuring, you'd want a larger aperture. But where the problem comes in is if you're scanning color, you should have at least 2 times the size of the aperture as your smallest patch size. So if you want to scan a color bar and the aperture of your instrument is 4 millimeters, you should not have patch sizes any smaller than 8 millimeters. And so now if you're using the instrument in an automated fashion, instead of being able to get by with a real small target, you've got to have a much larger target, which takes up larger space on your printing device, and it becomes a little more challenging to image in multiple ways. So aperture size is an important part. Another key part is knowing that your instrument is actually measuring correctly. So with ChromaChecker, our first tool that we introduced was called Instrument Inspector. And Idea Alliance still sells Instrument Inspector on Idea Alliance's website because they feel it's such a critical part of the puzzle. So many people measure color today, and they're not knowing that the instrument that they're using to measure is actually right to begin with, which is insane to me. So we have a procedure where you can, what we call baseline, virtually any instrument. And we use what's called a T42 target, which is actually built in the ISO 23021 specification for monitoring and tracking spectrophotometers over time. There's only 2 targets in that ISO specification. One is our T42 target, and one is the BCRA tiles, which are available for tens of thousands of dollars. So ours is a very reasonable way to track your instrument and know that your instrument is measuring correctly. And the concept is, the first time you measure the target, ideally the instrument should be new or recently certified, and then you can set up a schedule to remeasure this target, let's say once a month over time, and ChromaChecker will check that the consistency and accuracy of this instrument is within your expectations over time. So that if let's say you have tracks within your ChromaChecker system that have a 3E factor, meaning you're expecting the color to match between, let's say, your Epson and Grackle within a 3E factor, if the instrument falls outside of 20% of that, meaning the instrument comes in at, let's say, a 20% of 3 would be a 0.6, we're going to flag that instrument saying this instrument is not appropriate for the type of work you're doing. So in this way, you don't get yourself into a situation where the instrument isn't precise and accurate enough for your type of work. Next, we have to at least talk about fluorescence and understanding that a lot of materials have fluorescence, and you need to, in many cases, pick up the quality and the level of fluorescence. But this slide, I'm actually showing the inconsistencies between how different instruments measure fluorescence. So here we've measured the exact same sample with an i1 Pro 3, an i1 Pro 2, an exact in M1 with part 2 export on, an exact in M1 with export off, and a Teshcon SpectraDens. Look at the difference in the OBA indexes between these different instruments when measuring the exact same material. And so the point to this slide is, yeah, we have things like M1 to better measure optical brighteners and other things that fluoresce, but understand that a lot of the math that goes in terms of calculating the fluorescence is interpretation. And different vendors, and even as you can see, even though we've got 3 X-ray devices here in 4 different conditions, we've got some very different values in terms of the OBA. So capturing fluorescence the way the eye sees it is still very much of a challenge. And sometimes it takes experimentation to find out which measurement mode will do the best when measuring fluorescence. Our spherical spectro, it actually has a fluorescent light source built in, so we can measure D8 sphere data, both spin and spec, with and without UV, which I don't know of any other hardware company that has that built in, but it becomes really valuable when we're dealing with certain types of fabrics that have optical brighteners in them and cannot be measured with a typical 45-0 instrument. Now, how do you check if your material has optical brighteners? Well, typically, if it's flat and consistent, you can use a 45-0, and then you can use a, we have a capability within ChromaChecker where you can, using our capture tool, which drives the 45-0 instrument, you can measure all the M conditions. And if you take the M2 versus M1, that gives us the fluorescent index of that material. And the higher that index is, the more fluorescence is in that material. So this is a key part. In addition, if the substrate is contoured, then you typically don't want to use a 45-0 instrument. You want to use more like a D8 degree sphere. And then again, using ChromaChecker capture, driving the D8 sphere, you can tell it to measure all 4 measurement conditions, and then it will automatically compare what the UV measurements are compared to the non-UV measurements and give you a rating for how much fluorescence is in this material. This then becomes very useful to know whether or not you should measure your production samples with or without UV light to illuminate that fluorescence. All right. Now, guys, feel free to ask questions at any point. Since we are doing this live, I was thinking I was going to have to do this tape, but since I am live, feel free to get the questions coming in. Beth will help interrupt me if there's any questions in there. So some more general rules. in measurement mode, 45-0, I would say all things being equal, typically use an M1 condition. M1 is the current state of the industry, which has some UV in the light source, which accommodates the ISO 3668 lighting condition, which has UV in the light source. So go ahead and do this. But if the material has a lot of optical brighteners, it really fluoresces on you, where the lab value, the B value in the lab numbers more than -8, you might want to consider measuring M2. I've got a number of customers using M2 because there is a limit to how far M1 can really accommodate the fluorescence in the material. And in talking to my counterparts in the industry, we typically hear between -6 on the B to -8 on the B is about the limit that that the M1 condition will capture a good rendition of how our eye is going to see the color. And depending upon the material you're dealing with, if it has a certain sheen property to it, and if we have any fishermen out there, you only use polarized lenses on your sunglasses when you fish, because on the water, depending upon how the sun is bouncing off the water, there's a sheen that interrupts our ability to look into the water, where a polarized lens on our sunglasses cuts through that sheen, and you can see 5 times, 10 times further into the water with a polarized lens. I remember the first time I was fishing in Alaska, my buddy's brother, he was using polarized lenses. We didn't know about them, and he was catching way more fish than we were, and he wasn't sharing the secret until we figured out one day. We borrowed his glasses and we're like, no wonder he can see the fish. Well, the same concept can be true with an instrument. So the instrument can have a polarized lens on it, and I've seen multiple materials where it's got a certain sheen on it at a certain light source, where the instrument, like an i1 Pro 3 regular, isn't picking up the actual color because the sheen is interrupting how the light is making it back into the receptor. Whereas the i1 Pro 3 Plus with the polarized filter can actually pick up the actual color. And we've got samples that we're going to be adding to our website to show this actual occurrence. So now let's go through a sample classification of determining which instrument to use. First, if the sample falls into a category where it's flat, it's matte, it's uniform color like ink or paint on a flat, even surface, chances are you're going to use a 45-0 instrument. And the one thing you should do is check for fluorescence. But if the material is flat and super glossy, or it has a textured surface with shadows in the surface, like popcorn ceiling, or a roughness to it, or fabrics with a real thick weave, like a ugly Christmas sweater that you're going to be wearing in a month or so, then that might not work so well with a 45-0, but you can test it. And we're going to show you how you test it with 45-0 to see if it works. Other types of surfaces where you have a multi-layered effect, like acrylic, or where you're printing on the bottom of of plexiglass, and you're having to measure through even a 1/4 inch of plexiglass to measure the color, a 45-0 typically will not work well in that scenario. So in these types of scenarios, you can use our 3-step process to see if the 45-0 will give you an accurate result, a precise result. And if not, then you typically will need to try a D8-degree sphere instrument to measure this type of material. In addition, if you're printing on mirrored surfaces like foil or gold or silver, aluminum, metal, mirrored surfaces, don't even try to measure it with a 45-0. It's not going to work. You'll want to jump right to a sphere. And we've got some samples on our webpage that actually go through this. In fact, let's do that now. Let's I'm going to quit out of the slide and go to our website so you can find where some of this is. Let's go to here's our here's a new page on our in our manual on our webpage called Instrument Geometry, what you need to know, kind of a summary of what I've kind of shared with you so far. But here's test one without an instrument. So this print is on an actual foil material. It's our CC224 target. And I actually made this sample and it works really well. Take a piece of paper or cardboard and put black on one side, tape white on the other side, and then punch a hole through the middle. And when you use your eye to put it maybe an inch above the target, and when you look through the hole, you'll see the color of the target as you would see without this sample in front of it. So it's going to look normal because on the backside is the white, and the white is reflecting the color, so you see it through the hole. And this simulates how a sphere instrument is measuring the mirrored data. If you take the black side of your paper, turn it upside down, look through the hole onto the target, you will typically see just black. You will not see any of the colors of the target. And you can show it to your friends and family. It's kind of a magic trick because you wouldn't expect this to happen. But what's happening is the light is not reflecting up at an even angle, so it's not coming back into your eye. It's getting trapped by the black of the backing of this material, and therefore you're not getting an accurate representation of what's actually on the target. And to show this, we took our ChromaChecker capture and we measured this foil material, the white or the foil, the base foil material using an i1 Pro 3. And you see the i1 Pro 3 saw the foil material, which you could argue is a bit gray. It saw it as black, where the CC sphere, a D8 degree sphere spectral, saw the foil as pure white in spin mode, and in spec mode, it saw it as more of a gray. And in spin mode, it's really simulating what your eye is seeing when you're looking through this piece of black and white paper with the white facing the target, the black facing you. This is really spin mode with a D8 sphere. Whereas on the right, this is really a 45-0 instrument in terms of measuring the foil target. And again, we want the instrument to simulate what our eye is how our eye interprets the color. And so this is a great little exercise to help you understand why you need a sphere instrument. And if you look at how a 45-0 measures cyan, it's not cyan at all, it's black. But the D8 sphere in spin mode is seeing the cyan as how our eye sees the cyan, as a real cyan. But in spec mode, it's not seeing it in a correct manner. So this is a neat little article, and I would encourage you to make this little sample with the white black backing with a circle in the middle and do this example. It's one of those neat tricks that your eye plays on you. So with that, let's go to, yes, Beth.
We have a question. What if you're printing on the top of an acrylic and not through it?
If you're printing on the top of an acrylic, you might get lucky and be able to use a 45-0 sphere or a regular 45-0 instrument. But in a few slides, I'm getting to this 3-step process that you can use with your 45-0 to know whether or not you can get away with it. Okay, so the last bullet here is metallic and pearlescence type colors. This again is a scenario where I wouldn't even try to measure it with 45-0. I try a sphere, and if the sphere doesn't work, I might have to test to see if a multi-angle will work. Okay. Now, here's that 3-step process. So for the person that had the question about printing on acrylic on the top level, do you need a sphere or can a 45-0 work? So we've built this simple 3-step process to help you determine that. The first step is put your instrument in one location on your material and measure that spot at least 10 to 12 times, not moving the instrument at all. So if you're using ChromaChecker capture with whichever 45-0 instrument you have, you can start the instrument by pushing the button on the instrument itself, or you can push the measure button within capture. And in this way, there's no chance of you moving the instrument. So I really recommend in this first step, you don't want to move that instrument one millimeter. Keep it in the same spot, hit the measure button at 12 times in a row within the variation tool. So within ChromaChecker capture, in our quick checker module, you have the ability to do a check variation. And what check variation does is it allows you to measure the same sample multiple times in multiple ways. In this way, I'm saying don't move the instrument. And then it automatically tells you what the average peak, standard deviation, and 95th percentile difference is in the measurements that you've made. And if the delta E's are high in these measurements, then you know that the instrument you're using is not appropriate for the material that you're measuring. So that's step one. Step two is you measure 9 locations on the sample, offset by typically about a ½ inch, keeping the instrument in the same orientation, again, using the variation tool within capture. And again, look to see what the delta E numbers are on those 9 different measurements. If it's a fairly high number, then you know that instrument is not appropriate for that material that you're measuring. Step 3 is measuring the same location, but rotating the instrument in roughly 30-degree increments. Think about the numbers on a clock, and see if the delta E's of those measurements are close to one another or if they're far apart. Because again, that will tell you whether or not this instrument is appropriate for that type of material. So let's go back to step 1. How do you know if the measurement fails? And it's if the delta E numbers are low, then you're safe to use that instrument. But you'll also want to try different options. You'll want to try M0, M1. You'll want to try with UV, without UV. Try different apertures if you have that available to you. So if the settings and the geometry and the aperture that you used the first time don't fail, go ahead and try the different settings. If you're using an i1 Pro 3 Plus and you're in M1 and it failed, go ahead and try sample 1 in M3 and see if it passes. And in this way, as long as the delta E's are small, you're good to go. If the delta E's are large, then you know that, you might have to buy a spherical instrument to do this type of measurement. And if we go to step 2, it's the same type of thing. When to know when it's outside the instrument. Now let's pop back to our website, because we also built a new article on this concept, applying measurement methodology to 3 different substrates. And as we take a look at this, so that's the name of this article. You'll see the date is today, because I was editing this article this morning in prep for this presentation. And we were only able to get 3 instruments to get readings, but we're planning on adding more data from more instruments. So we did an i1 Pro 3, an Exact, and a CC Sphere. And we measured this material. And what we're looking at here is these calipers are at ½ an inch. And at ½ an inch, you can't really see what the texture of the material looks like. So down below here is a zoom in of what this material looks like if you look at it closely. And so we talk about measuring the material for fluorescence and optical brighteners. And you can see that with the textile A, B, and C, so this is A, B, and C, you can see that the B is -7 on textile A, the B is -12 on textile B, and the minus B on C is 10. So very high levels of an OBA index. So ideally, you'll want to use some sort of light that accommodates the OBA to accommodate the visual appearance of it. And then we're looking next at the printed black density. And when we look at the printed black density, we can see that the density differences between these samples is quite extreme. And you wouldn't expect it to be. You wouldn't expect, if you printed black ink on these three materials, that there would be a whole lot of difference. But there is quite a bit of difference in these materials, because if we go to the black, you can see that the L star on textile A is 23, the black on textile B is 28, and the black on textile C is 18. So the black ink on textile C, which again, if I zoom back out and look at textile C, the black ink on textile C is the darkest black that you have. And B is the highest or the lightest black of all the samples. And the reason is that you'll see the black ink wasn't able to make it into all the crevices of this sample. So when the instrument measures the color on this sample, there's a certain amount of white that makes it back into the instrument, which corrupts, if you will, the level of black that is being perceived. And this is one of those scenarios where maybe implementing our average color versus dominant color would come into play, because to your eye, it looks pretty black, but to the instrument, it's 10 points lighter than the other substrate. And of course, we should really do some due diligence on the substrate to really know which instrument we should use. Now, here's using the i1 Pro 3 in the 3-step process. So in step number 1, we measured textile A, B, and C multiple times. And using the start variation tool within Capture. And you can see, if I zoom in here, we measured 9 times on textile A, and our overall E factor was very low for the substrate white. And we did the same with B, and again, it's very low. So passing, great. We can use a 45-0 in terms of measuring textile. Textile C, same thing, very low, 0.2. Now, as we go to the printed black, we can see on textile A, again, 0, very low, B and C. So in this way, step 1 passes in using a 45-0 to measure these 3 types of substrates, because the E factor is so low that the instrument is measuring consistently between these materials, both black and white, and therefore we can say that at least with step 1, it passed. Now, the next thing, and by the way, this video just shows how the software works. We won't take the time here to show you. You can go to the video if you want to see how it works in doing the variation on this. Now, step 2 with the i1 Pro 2, we go ahead and we measure the substrate and the printed black again. But this time, if you remember, we're measuring in different locations on the sample. We're not measuring the exact same location. And now you start seeing higher numbers. You see the 0.11 E factor versus the 0.02, and you see the 0.16 versus 0.03. And on textile C, look at this, the 0.45 on black. Well, if you're trying to measure textile C and you're trying to get color to match within, let's say, a 2 delta E, you don't want more than 20% of the error resulting from a variable in the substrate. So you take 5 times the 0.45 and you're at a delta E of 2.25. You're at 2.25 delta E just due to the variation of how the instrument is measuring that substrate. this substrate C is not appropriate to be measured with an I1 Pro 2 if you're looking at even probably a 3 delta E of a color match. If you're dealing with a 6 delta E of a color match, meaning your expectation factor is more like a 6 E factor, then okay, you could use an I1 Pro 3 to measure textile C. So here we're using your expectations for a color match based on our E factor exercise, which in review, if you're new to us, please go to our website, the homepage of our website. Let me just go there now as a new page. And on the homepage of our website, you can go in and see what your expectation factor is. And you can do the exercise, which will show you a number of samples. And what you do is you choose whether or not those differences are too big or too small. And as you go through here, you make these decisions. And then at the end, after so many decisions, it says, hey, your expectation is an E factor of a 3, which is very tight. So you're expecting very high quality. And if you have that level of expectation, then measuring that textile C is not appropriate for your work. But if you were to take that exercise and you came out at more of a 6, then yeah, you could probably do textile C in terms of a 45-0 instrument. In this case, we would then do this with the spherical instrument. And if I just jump down, and by the way, here's the printed black that I was describing, where the printed black isn't making it into all of the texture. So there's white spots in here, which corrupts how the instrument is interpreting that color. And here's a video that goes through that. And then here's step 3 with those textiles again. And again, in textile C, you see some pretty high E factor numbers here, which leads to the conclusion that you might want to be using the CC sphere instrument to measure textile C. Now, we're still gathering the numbers. Stay tuned. This page is going to be populated more by the end of tomorrow with the actual E factor numbers when measuring these same substrates with both an exact and the CC sphere, so that you can see that this is a real scenario where in textile A, you can actually get by with 45-0, but in textile C, you really should have a sphere instrument. Okay, I see there's more questions in Beth. Any questions relevant to this 3-step process?
No, I just added the link to the page. That was what was requested.
Oh, great.
That you were just on.
Yeah, thank you for doing that, Beth. All right, so our hope here is that this 3-step process, well, before I get to the 3-step process, you do need to understand that the substrate is the 5th color and 4-color printing, like everything else we do. So you need to understand that the makeup of the substrate can greatly affect the results, as I hope that sample I just showed you proves. So even though the substrate might be uniform when raw, it might not be uniform when printed. So keep that in mind when you're choosing your samples and when you're doing this 3-step process to determine whether or not your instrument is going to be precise enough to give you a repeatable numeric value that will help you do your process control and your color management to get the color to meet your expectations. So in summary, we're really hoping that this 3-step process in ChromaChecker, using ChromaChecker Capture's variation tool, will help you make better decisions in terms of when to use which instrument with which material. As I've mentioned, this is the beginning of an education for everybody. We're learning too. And we're excited to apply different materials to this methodology and document our numeric values so that you can see the effect of light and instrumentation on different materials, so you make better choices on which instrument to use when. And as I said, stay tuned on this page, and please, if you have samples that you're struggling with, please send them to us. We actually had a couple customers this week, or within the last week and a half, have some samples where the material on the sample was a pattern type effect, and they were having a tough time capturing a flat color to match the visual effect of the pattern. And these are the very things that we're trying to help our customers solve with ChromaChecker. So please feel free to send any samples to us, and we're going to be happy to publish this data and help everybody understand how this works. So we're coming up on 50 minutes. I've got a little bit of time for any Q&A if anyone has any questions for me at this point. Sounds like there might not be any questions quite yet.
Yeah,
So,
we've got one. How about dye subcolor measurement, for example, on ceramic and on polyester?
well, yeah, dye sub on both polyester and ceramic is a very challenging material. And this is the absolute case of applying our three-step process to that material. So print a typical color bar on that material, and then apply our three-step process with whichever instrument you have today. And if the E factors are high, then you know you can't use that instrument. And again, exhaust all measures. Use the instrument in M0, M1, M2. If it has M3, try M3, and see which settings give you low repeatable delta E/E factor values, so that you know that the data that you're capturing is consistent. If the data that you're capturing from your material is not consistent, you really have no chance of building a G7 curve or building an ICC profile to represent how that material images to the eye. So use this three-step process. And by the way, those links, the link to the page that I had, they have the video. So let's just actually play the video of, in this case, using an i1 Pro 3 and measuring the same sample, and then just rotating that sample 30 degrees, like every clock position. And within capture in start variation mode, you can see in this case, let me zoom in here. Let's make this video bigger. You see how these dots are far away. We're a 0.223 E factor already, which is a fairly high number. And you can see that the distribution of the colors of the measurements are not in one tight bullseye. They're spread out on the B axis here. And it's due to the directional qualities of this material that's being measured. And in this way, you can make a decision saying, you know what, I can't use my i1 Pro 3. I need to use potentially a sphere instrument, or maybe a i1 Pro 3 Plus, which has the larger aperture and has the polarized filter on it. So I hope that answered that person's question, because this is what this session is all about, is printing on unusual materials and ensuring that the instrument that you're using will capture the characteristics of those materials in a way that simulates how your eye captures that material, and therefore you know that you'll have a good solid methodology to build your curves, build your profiles, do your process control, to know that you're reproduction of that color or ink on that substrate is going to give you what you want.